In this lesson, we're going to discuss single displacement reactions. So these are reactions where you have one element that's part of a compound gets displaced or replaced by another element. And you can have two different types. Okay, so you can have where you have a metal reacting with a compound, and the metal is going to replace the cation in the compound, which will generally be another metal. And that can be represented by A plus BX, making AX plus B. So you can see the A and the B are switching positions, and the A and the B are both metals. So here's an example. Magnesium plus zinc chloride creates magnesium chloride and zinc. So the magnesium and the zinc have switched places. The other type of single displacement reaction involves the halogens. So a halogen can replace another halogen as an anion in a compound. So these kind are represented in a generic sense like this. AX plus Y creates AY plus X, where X and Y are the halogens. And here's an example. Calcium bromide plus chlorine is going to make calcium chloride plus bromine. So in this case, the bromine and the chlorine have switched positions. So first, let's look at the first type, the single cation displacement, which is represented by A plus BX makes AX plus B, where A and B are the metals. So different metals have different reactivities. So in other words, some metals can't displace another metal cation from a compound. Sometimes A can't kick B out of the compound. So as an example, iron can displace copper. So iron can kick copper out of its compound and take its place. But copper can't do the same thing. Copper can't kick iron out of a compound. There's no reaction. So how do we know when the reaction will occur and when it won't? So for this, we need an activity series. So an activity series is shown on the side of the screen. It lists all the metals in terms of their reactivity. So at the top is the most reactive metals. So in this case, lithium is the most reactive, and then the least reactive at the bottom. In this one, it's gold. So a metal will displace any metal in a compound that is below it in the activity series. So lithium can displace pretty much anything, and gold can displace pretty much nothing. So how do we predict the products of a single displacement reaction when we're just given the reactants? So you're going to ask yourself a question. Is the elemental metal, so that's the metal that is not part of a compound, higher on the activity series than the metal cation that's in the compound? If the answer is no, then you're just going to write NR, which is no reaction. If it is higher, then the reaction is going to occur. So you're going to switch the positions of the metals, and then you're going to create the new compound by using ionic charges, and then you're going to balance. So let's look at some examples. So we're going to determine if the reaction will occur, and if it will occur, we're going to complete and balance the equation. So we need to ask ourselves, is iron higher on the activity series than chromium? And in this case, the answer is no. Iron is below chromium, so there's no reaction. Next example, zinc plus silver fluoride. So is zinc higher on the activity series than silver? In this case, the answer is yes. Zinc is above silver, so the reaction is going to occur. So zinc's going to pop silver out of the compound. So there's silver. And then zinc and fluorine are going to create a compound. And so you need to think about their ionic charges. So zinc has a charge of 2+, fluorine is a 1-. Do our crossover, and we get ZnF2. And now we just need to balance. So we need 2 fluorines, which now gives us 2 silvers. A note about states here. So you'll notice that the ionic compounds in the reactants are aqueous. So these reactions occur in aqueous solution. And so the ionic product will also be aqueous. Next example, aluminum and tin 2 nitrate. So is aluminum above tin? Yes, it is. So now we have some pure tin being made, and aluminum is combining with nitrate. So we get their ionic charges, cross that over, AlNO3-3. So we've made tin and aluminum nitrate, and then we need to balance. So we're going to need to put a 3 here because we need to balance out the nitrates. So a 3 there and a 2 there to do that. And then we need to balance the tin and the aluminum. One more. Is mercury higher than sodium? The answer is no. So mercury is below sodium, so there's no reaction. Okay, on this activity series, you will see hydrogen. And hydrogen's not technically a metal, but as we've discovered in other situations, it can behave like a metal because it can form a cation. So let's look at single displacement reactions that involve hydrogen. When hydrogen is in a compound other than water, those will be acids, right? It can be displaced by metals that are higher than it is in the activity series. So in that way, it behaves just like everything else. If something's higher, it can displace the hydrogen. However, when the reaction involves water, we're going to treat water as an ionic compound, right? So we're going to break it down into, change the H2O into an H plus ion and an OH minus ion. And only the metals right at the top of the activity series, so lithium to sodium, those are the only ones that can displace hydrogen from water. So if we look at some examples, cadmium plus hydrogen carbonate. So this is hydrogen and it's not in water. So we're just treating hydrogen just like all the other metals. So we ask, is cadmium higher than hydrogen? And it is. So the displacement is going to occur. So cadmium is going to bump out hydrogen. And remember, hydrogen is a Hofbrinkel element, so it's always going to be H2. And then we're going to make a compound containing cadmium and carbonate ions. So we'll cross those over, and that's going to look like that. And that one is already balanced. So here we have magnesium and water. So we have hydrogen in water. So we have to look and see if magnesium is high enough in the activity series. And it turns out that it is not because it is below sodium. So there's no reaction. So now how about if we try to react barium with water? So barium is high enough in the activity series. It's above sodium. So this reaction is going to occur. So we remember that we need to think about water as this ionic compound with H plus ions and OH minus ions. So the barium is going to bump out the H plus ions, and they're going to become hydrogen gas. And then the barium is going to combine with the hydroxide ions. So barium ion, 2 plus, combined with hydroxide ion, 1 minus. So we get BaOH2. And then we just need to balance, which we can do with the 2 here. And it's all balanced. Now, the biggest mistake that's made here is when you're taking barium and displacing the hydrogen in water. Students tend to want to put the product as barium oxide, right? Barium comes in, pops out that H2, you're left with BaO. Okay, so you have to be careful there to remember that you have to treat the water as a hydrogen ion and a hydroxide ion. So now if we look at single anion displacement, so this is the halogens. So AX plus Y makes AY plus X, where X and Y are halogens. So we again have an activity series for the halogens, and it's exactly what's on the periodic table. So you won't be given a separate halogen activity series because you always have it. It's right on the periodic table. So a halogen will displace another halogen if that halogen's in a compound and it's below it in the periodic table. So fluorine can displace bromine because fluorine's above bromine, right? So sodium bromide can react with fluorine to make sodium fluoride and bromine, but not the other way around, right? Bromine can't displace fluorine because it's below it in the periodic table. So if we look at some examples, so first we've got magnesium iodide reacting with chlorine gas. So we check, is chlorine higher than iodine? Yes, it is. So they switch places. So the chlorine's going to form a compound with magnesium, and then the iodine is out on its own. And don't forget the 2, because iodine is a Hofbrinkel. All of the halogens are. And then the next example, aluminum fluoride plus chlorine. Not sure why that chlorine is a liquid, should be a gas. So then you ask yourself, can chlorine displace fluorine? Is chlorine higher? Well, it isn't. Chlorine is below fluorine, so there is no reaction. So those are examples of all the different types of single displacement reactions and how you can figure out whether they will occur and what the products will be.